Uh, Hi everyone. Today I will be talking about improving diffusion models on specific domain. Specifically, we will be talking about generating game assets for mobile games. The reason we decided to pursue this is because currently the mobile game market is absolutely huge. For example, in China, it currently values about $39 billion, and at the same time, it's very oversaturated, which leads to accelerated development times and drop of quality. But the demand from people is forever rising quality. At the same time, the invention of good generative models in 2022, like Stable Diffusion, DALI, led to drop in Illustrator jobs by 70%, which is huge. So this is very relevant topic. So our aim is to decrease the amount of human errors required to create visually consistent game assets for art-heavy games such as card games or gacha games. And we want to be able to, from a small initial set of images, like 10 to 50, generate many more, such as 100 or 1,000 or 10,000 pictures. Before we can generate something, we need to decide on a metric to see how good we did our job. And here we present all of the basic methods that you can use, such as inception score, Frechette inception distance, and kernel inception distance. These three are all based on inception model. Then there are also clip aesthetic score, which is basically clip embeddings and the regression model trained to predict how people evaluate the artistic value of the image. And we score the whole dataset and find the divergence between two generated sets of data. Also, we tried to modify FID to fit our needs better, because FID was trained on ImageNet, which did not contain any animate pictures. So we decided to swap inception model for Deep Dunbarrow, which is a classification model made for animate pictures. The result, how we evaluated each metric, is that we have some expert ranking. We generated 8 different datasets. You can see the example on the left of images from each dataset, and asked some expert to rank them, how they think, how far they are from the original dataset. And as you can see, the FID and FDD are the best metrics, but we decided to use FID because it's like one of the standard metrics in data science. And next, we need some data to train on, and we decided to pull it from some game. The general problem of our task is that they don't have enough data. For example, in this case, we only had 1,200 images, and we split it for train and test on about 1,200 pictures. The FID of test split versus train split is about 80. Also, each character in the dataset had some features, such as element, weapon, and rarity. You can see the rarity on the left. As the rarity increases, the amount of detail on the character image rises. And the element describes the primary color of the image. So fire is red, water is blue, and so on. One of the problems with our chosen metric FID is that it requires quite a lot of samples to get the accurate results, which we don't really have. Because with less images, it produces large dispersions, like with even one image more or less, it can translate to large variance in the FID metric. So we settled on about 240, as we can't really pull more because we need also some training data to train. So all of our results might be quite noisy. To establish a baseline, we decided to take a stable diffusion checkpoint fine-tuned on anime-style pictures and run our test split through image-to-text classification model, deep number we talked before, to obtain the description, and then generate with the stable diffusion all of our images. The FID of such approach is about 300, which is not good. And as you can see, the style is not transferred at all, which is quite expected. So we turned to different other approaches. So first we tried DreamBooth, which was proposed in Imogen. It's green on the slide. But it didn't satisfy us because it's hard to work with, because every time we want to train a new model, it produces a huge file at about 2 to 4 gigabytes. It also cannot be used on different underlying checkpoint, and we can't use multiple of them together. But the quality of produced images is quite high. Next, we tried textual inversion. It's very easy to work with because it produces a very small files, such at about 2 to 6 kilobytes. It also can be applied to different underlying models and we can use multiple embeddings together. Textual inversion, basically, we create an additional embedding, which we train to represent the initial data, so that model, when we use this specific embedding, knows what data we want. And the last approach we found is low-rank adaptation. It's an approach that came from large language models, which are notorious hard to fine-tune. And it combines both good qualities of DreamBooth and textual inversion, because it's easy to work with, but at the same time, it produces a lot better quality than textual inversion. First, we tried to see how much actually data we need to translate style. So we tried different dataset sizes, and as you can see, even with the dataset size 10 is enough to get a good FID. For example, in this case, we got an FID at about the same at dataset size 10 as with dataset size 240. Also, we observed that model saturates at about 480 pictures. So adding more doesn't improve the results. So here you can see the example of images produced by models with dataset size 10 and 1000. It's hard to judge which is better, because in general style is transferred, but every picture lacks smaller details that are present in the initial dataset, so it's very hard to judge did we achieve our goal or not. Also, when we trained our models, we always used early stopping, so we try to see can we achieve the stopping point at when it stopped improving. And what we found that at about 400 epochs, the model start produce FID drops, but at the same time, the visual quality of the picture becomes very bad. So here you can see the original picture. This is the picture produced by a model with quite bad FID, but at the same time, it's quite visually appealing. And this is the picture produced by the model with the best FID score, but visually it's very bad. And next, we try to see how good LoRa generalizes our dataset. As you can remember, there are several features such as element, weapon, and rarity. Here I focus on element only. At dataset size 10, it didn't learn at all. it doesn't distinguish between elements. At that set size 100, it learns something about elements, but often gets them wrong. But with the luck, you can get the result you want. And at about 500 pictures, model distinguish between elements completely, which is good. But at the same time, even when we trained our model on the whole dataset, it did not learn how to distinguish between rarities. So on the left at the top, you can see how rarities distribute between in real dataset, and that the model didn't learn it at all. But with weapons, it's a lot harder because it learned something. For example, magic is different from slash or bow, and bow is different from blunt. But pictures lack smaller details, so it's hard to tell if it learned correctly or at all. Also, it's important to mention that LoRa can be used not only for characters, but for other game assets as well. For example, we try to train it or to generate weapons and some accessories. And as you can see, even when underlying model could not generate them at all, the produced results are quite good. Some downsides of this approach is that in general, it decreases the details compared to the base model. Also, it's very easy to overfit, and it can cause visible artifacts. As you can see on the left picture, some squares there. And the model requires solid stopping, which means that we can't just use grid search to get the best results we want. But all of this can be tackled with human input. So if there is a human in the loop, we can adjust prompts and parameters of generation, which leads to a lot better results. As you can probably see, this is the original picture. This is only with LoRa, without any cherry picking, and this is picked by me. So I generated about 100 pictures and just choose the best one, and the results is a lot better, I think. So our conclusion is that FID is a completely non-relevant metric for this task. It's hard to apply it here. Also, a small number of pictures is enough to approximately recreate a style, but the general quality of produced pictures is often not good enough to use in production environment. But we can bring a human assessment or input to bring the quality up to the production environment standards. Also, we need a lot more research in the subject, especially investigating or creating appropriate metrics for this task. And also, this approach could be applied to a wide variety of domains, not only chart generation, but almost anything like icons, backgrounds, whatever. So thank you very much. I know, do I have like another 2 minutes?
Yes, you do.
Okay, that's great. Then let's have some interactive part. I would like you to guess which of the pictures was generated. Was it the first one or was it the second one? Because I can see the audience, I will just tell you. I'll give you like 5 seconds.
I can count and tell you. So please, if you think that the first one, raise a hand. Okay, which one was generated? The first one, how many? 7. And the second one, 3. So the first is 7, second is 3.
Clearly, you didn't all pay attention because the second one is generated. So once again.
Okay, once again. So the first one, please raise your hands. Okay, now everybody is in doubt. Nah. The failure was bitter. Okay, anyway, let's vote. So the first one, the second one, 3, 4, 5. 5 hands. So now we have 0 against 5, and so many people decided not to.
Yeah, you guessed correctly because the second one was generated. Again?
Okay, so the first one, 1, 2, 3, 4. 5 hands, and the second 1, 2, 3. So 6, 3.
You guessed incorrectly. The second one is once again is generated. So it seems that we don't even need the human input to get a good results, because clearly it's hard to tell which one was generated. So okay, I will now answer your question if you have any.
So yeah, thank you. Questions? Okay, I have several. So first of all, on the slide 9 or maybe 10, you said that you used some data for for test. You said like the data set is small. Yeah, you used only
240 pictures for test.
But what do you mean test here? Like once we talk about generation.
Test split. So we have a whole data set at 1200 pictures, and we take 240 of them and say that this is a test split. Basically, how we test is that we get the description of the picture plus additional information of the features, and run it through our model to get the the modified picture. And then we calculate the FID between the test split and our generated images.
Okay. Yeah, I see. Now maybe a little bit tricky question. So could you please compare how much money you spent on this research versus how much money would be spent for the painters?
Oh, actually, we didn't spend a lot of money because...
I mean, you work for free, right?
Well, we did this research at about like 1 month, and we used 2 VSTOR. So we have working 2 people. So let's say it was about $10,000 to $15,000 to get this research done, and the illustrator jobs at least in China, because this is the market we are focusing on, cost at about I would say about $3,000, $2,000. So we probably spent like 5 to 6 months of illustrator job time. But at the same time, illustrator can produce like, I don't know, maybe 50 pictures, 100 if he is very, very fast at the same time. But we can generate like 1,000 more or 10,000 in just one evening.
Okay. Okay, thank you. I actually didn't expect you would answer, but yeah, this is quite a good estimate. So, and if there is no one else who wants to ask, my last question is, so actually we see that the network doesn't capture the style really well. So it captures the style, but not precisely. And I believe if many people would use the very same technique, maybe we would have very similar looking images of the very same style. So now we have anime, it has like several, let's say, ways of how to draw anime people. And if not only you, but 4 other studios would use the same, maybe we would have the very similar pictures in different games.
Well, no, because what we're focusing on is that we don't want to completely eradicate the illustrator job market. And as we imagine it, is that the studio have like 2 or 3 illustrators on pay, which generate, which draw the first initial pictures, like 10 to 50 that perfectly match the style of the game they want to create, and then they send these pictures to us, and we train a model to recreate the style. So it's less about like recreating the same style. It's more about how creative are illustrators and how good we can recreate the style they created.
Okay, yeah, thank you. That's the good answer. And thank you for the talk.